but probably what I have to do is probably an important video. I think that's bright enough to see without turning lights off. If it's not, let me know. So, what screen do I want to share? Probably want to share. Can find Google Drive will be a good shape. I'll just say there's another folder there. Yeah. Okay. So we can go ahead and get started. Again, I'll stand over here, so hopefully the video will be better than, or the audio will be better, okay? So we're reviewing for the exam today, okay? The exam will be on Monday. So if I've got the chapters here as if you had the book, you don't have to have the book, but hint, the book is online. There's a PDF of it if you want to find it. In addition, I've put up notes for most of this, okay? So I'm going to go through the basic topics that are going to be on the exam. Ask questions along the way if you want, or save them to later, whatever you want to do, okay? And I'll work through a couple of examples as well, okay? So from the first chapter, the things we talked about the criteria that we're going to use throughout the class to judge different languages, okay? So the point here is, or the things we're looking at are things such as readability, writability, maintainability, efficiency, things like that. But as part of that, we're going to look at these kinds of features, okay? The first is the simplicity of the language. Okay? The simplicity of the language, just what it says, is it straightforward? Is it not complex, okay? Most of these things are two-edged swords. So simplicity is good until it's not expressive enough. If it's too simple, then it's not going to do much. It's too complicated, it's not going to be readable or writable or any of that stuff, okay? The orthogonality refers to whether a small subset of language elements could be combined in any way and you have a valid language construct, okay? Again, that could be good and it could be bad. Sometimes it will allow for things that make no sense to happen, okay? So you have to be careful about that. Whether or not the language has data types, well, I guess they all have data types, whether they are explicit or implicit, whether they're statically or dynamically typed, how many there are. In particular, languages often have different size integers you can use, okay? If you're on a big computer, plenty of resources, it doesn't matter, but if you're on a smaller system, The ability to have a 4-bit integer becomes important. Okay, so whether the language supports that or not can be important. Okay. Again, the syntax design, does it make sense how the syntax works? When you see a structure, does it work the way you would expect? Okay. Some languages do a better job of that than others. Support for abstraction. Abstraction is a key concept, okay? So you should know what that means. Abstraction in this case refers to the ability to talk about concepts without having to flesh out all the details. Okay, so we're talking about, so what's a good example? So if you're talking about a data structure of some sort, you can talk about a list without having to fully specify what the list is, okay? Think in C++, when we do the abstract data types, where we're creating some overall organizational class that we then will specialize into other classes. That's the idea of abstraction, okay? Expressivity is just how much you can do in the language, how many kinds of programs can you write? Is it strictly related to one problem domain, or is it available for a wide variety of things? Okay. Type checking, does it check for type? If not, where's that going to cause you trouble? Okay. Remember, every feature adds to the bulk of the language and what it takes to process and to write programs. So you just have to keep track of that. Okay. Exception handling. What happens when things go wrong? Are you able to get things back on track or not? Okay. And restricted aliasing. I have telegraphed the fact as strongly as I can. You have to understand aliasing for this event. Okay, so there's going to be a question on aliasing. It's that important. So again, aliasing is when more than one name point to the same memory location. Okay. It's a problem because it's not apparent to the programmer that changes made to one variable change another variable. Okay, so they really are problematic, and some languages don't have them at all. Some languages have total freedom to alias as much as you want. Okay. We also talked about the imperative languages, which are most of what we know. Those are based on the von Neumann architecture, okay, where the data and the operations on the data are stored in the same memory. Memory is not differentiated. The other kinds of languages are called functional languages. That's languages like Camel, Haskell, ML. We'll talk about those as we go along. Okay. And functional languages, they're based more on lambda calculus, which we haven't talked about so much yet. It's the idea, kind of like the reverse Polish notation that we talked about, where you don't really have variables. You sometimes do in these languages, but that's an add-on. It's that you're able to structure the operations in such a way that you don't need variables, okay? And everything's a function, including no name functions. So for a line of code, instead of an expression, you'll write a function that just happens on that one line, and you get some power from that, okay? In the last part of that chapter, we talked about the difference between compilation. When you compile a program like C or C++, it's going to go through and link to libraries to make a bigger program, and then turn that into machine readable code directly, okay? You also have pure interpretation, something like Python. In Python, it doesn't do anything until you start to run the program. Then as you're running it, it compiles it, not really compiles, but it turns it into machine code on the fly, okay? It doesn't do it in advance, okay? Pros and cons to both of those, okay? And then things like Java and Perl are hybrid systems, where it compiles not to machine code, but to some intermediary bytecode state, which can then be ran quicker. Okay. Chapter 2 was on the history, nothing on the test about the history. Okay, so that was just for us to talk about, but nothing big. Okay. And if there are questions, let me know. Why am I getting the little circle when I just want to go down? Oh, I'm on the wrong thing. You're on the wrong thing. There we go. So the next chapter, we talk about the difference between syntax and semantics, okay? Again, I'm going to make the assumption that you understand what both of those mean. Okay, the syntax, in essence, is the grammar of the language. Okay, it's in English, it's like noun-verb agreement. You know, it's like the tense of nouns, of verbs, sorry, things like that, okay? Semantics refers to the meaning of things, okay? So, and we'll talk about semantics more in a minute. A couple other terms here, we have the lexemes and the tokens. A lexeme then is the smallest unit we're going to talk about in our language, okay? It's going to be an identifier. It's going to be a literal, an integer literal. It's going to be a floating point literal. It's going to be the equal sign, okay? So the token then becomes the categories of things. Like, is it an identifier? Is it an integer literal? Things like that, okay? So we talked about how to go through the lexical analysis where you take an undifferentiated string of characters and organize them into which of these are variables, which of these are mathematical operations, which of these are whatever. Okay. So with that, yeah, you should know what those terms mean, and you should be able to work through an example on that. Okay. We also talked about the Bacchus-Naur form, okay, or the BNF, and that's basically where we're going to have it in the most canonical or most traditional form. We're going to have the angle brackets that have the non-terminals that have to be substituted for, and then we have things that are not in the brackets, which are the terminals, which are not substituted for, okay? So all of those BNF are going to have a series of grammar rules that define the language. And then you go through and you can do a parse tree or however you're going to do it. We'll do an example of that in a minute, to replace the non-terminals with terminals to generate all valid strings of the language, okay? So if you can't get from the grammar rules to a particular string, then that string is not in the language, okay? So that's how we define that, okay? So you should be able to create those. Again, on the exam, it will not be complicated ones, okay? And you should be able to use them to tell if a string is in the language or not, if it's accepted by the language, and to do a parse tree where you're going to go through. Again, we'll show an example. The other way we do this is using capital letters as the terminals, sorry, non-terminals, and lowercase letters as the non-terminals. That's just kind of a shorter hand way to do it, okay? And we'll look at some examples of that again here. Okay. So yeah, the grammars are just these sets of rules that allow us to determine whether a string is acceptable in the language or not, okay? Again, at this point, we don't care what it's doing. Does it make any sense what it's, we don't care, right? We care, does it have the form of a valid statement, okay, in the language, okay? We then move on. So again, parse tree, you should be able to create those. That's relatively straightforward. It will not be super complicated. Then we get to semantics, okay? There are three, I will say that the attribute grammar is in the book. We mentioned it briefly, will not be on the exam, so don't worry about that. Okay. But on the semantics, we talked about operational semantics. The operational semantics is you're tracking the state changes made by the code. Okay, so that's how you're describing what's happening to the code. Okay. The denotational semantics is the one that uses the mathematical expression to determine the meaning from the code. Okay. And then finally, the axiomatic, which I'm most interested in, read that as most likely get a question on, okay? It's the one that has the preconditions and the postconditions, and you're able to prove the validity of statements or programs, okay? Again, there certainly could be either a single sentence where I ask you to do the weakest precondition of, there could be a couple of statements in a sequence with a post condition, and I could ask you to work backwards on, okay? But no program verifications of loops or any of that stuff, okay? Because that's complicated. Okay, so that should be a relatively straightforward thing, okay? Again, the weakest proposition, maybe a thing, okay? And then I can ask you how the axiomatic semantics can be used to prove program validity without actually having to do the program validity. Does that make sense? So again, I haven't said it yet. I haven't made up the test yet, but I do have an outline of what I'm going to ask. Some of the questions will be problems. Some of them will be essay type, you know, this big kind of questions, okay? So I can ask you, for example, what's the difference between operational, denotational, and axiomatic semantics, okay? And for that, I would expect you to describe each one in a sentence or two, whatever you need, and then talk about the differences, okay? So some questions are the essay type, some are problem sets. So I could ask you, how can axiomatic semantics be used to prove program validity? That doesn't violate me saying I'm not going to ask you to validate a program, right? It's about how to do it, not the actual doing it. So make sure you understand the steps, but you're not going to have to do it live on an exam. Okay. The next chapter talked about the lexical analysis, which is the idea of going through some input string of characters and turning that into your tokens. Okay. Again, you should understand what regular expressions do. The pattern matching, I'm not going to ask you specific examples on regular expressions. Okay. So that's where we had the code. It's called front.c. So we also, the book, and I think we talked about in the homework, it seems like it is like a state machine. In fact, one of the homework problems was the / comment style of C++. What would a state machine look like for that? Okay. And just pop this up real quick. What am I doing? Okay, so if you're looking for that question, like you're trying to determine whatever that, okay. So as far as a state machine goes, you could be at a state like reading input, okay. You could move to a state, you can see that, yes. Where you get a slash, okay. That moves you to the state, whatever you want to call it, which could then move you to a state, and those aren't really supposed to be parallelograms, those are usually rounded boxes, but whatever you do is okay with me. So you then have that, okay. So this gets you to the reading comment section, okay. And then from there, if you get an asterisk, okay, it then moves you into this intermediate step, the line there, where if you then get slash, okay, it's going to move you back to there. Basically, you're done with the comment. But anything else is going to keep you in the state. Okay, so again, if I had like slash star hello star slash, okay, it would start off here with this first slash and move me to this state. This, if anything else, okay, so I guess that's the other thing. Anything else is going to go back from here besides the slash, okay, or sorry, the star. The star would take you to here for this one, okay, and then the H, E, L, all that keeps you in here. Then that asterisk would take you to here. That slash would take you back to the beginning. Okay, so it's this looping. Okay, the same thing for a variable name. When you see a character, is the character part of a keyword or is it part of a variable name? Okay, you would look for the keywords. Okay, so you would have, and we're not going to do all this, it would be forever, but you would have all of the keywords. Like if I would enter an F, okay, well, we know it could be a 4. Pencil really makes me insane, you know, if it's defective rule. So we could check for that. So if the first letter is an F, the second letter is an O, the third letter is an R, then we know we have a keyword, and that's the token, okay? But if it's an F followed by a B, then we know we're just in a variable name, right? And we would stay there until we hit a space, okay? And in that, for most languages, any numeral or any letter is valid, okay? So that's kind of what that's going to look like. Okay. So that's the part there of understanding how a lexical analyzer program would work. Okay. So that's getting us from the languages to the tokens. The next step is the parsing, where you're trying to figure out what happens on the code. That's where you get back to the BNF notations and the grammars and all that. Okay. Parsing is difficult because there are often multiple paths that lead to the same end, right? If there are there's enough power to the language, you can have lots of ways you could get there. Okay. So in a complex parsing operation, you're going to go down a path for a while and find out that was the incorrect path. You have to backtrack. Okay. It's that backtracking that makes parsing difficult. Okay. And it's led to these two basic approaches that are used to parsing. And the first is the top down. Okay. The top down is going to move from the smallest part of the things from the whole thing and go down to try to get the parse tree. Okay. So it's going to look for things that are in the initial statement to move forward. Okay. Where the bottom up is going to look at the result and try to build from that what rules must have been used to get back to it. Okay. So again, no problems on that top down or bottom up. Don't spend time on the details. Just understand the basic strategies there and how they differ. Okay. And then we get to the last chapter we covered, which is on names and binding and scope. Okay. So just the design issues you can have with the names. Do you allow case sensitive to be case sensitive or not? Do you have keywords that are only reserved if they're in the right place, or do you have reserved words that can't be used anywhere? Okay. And again, keywords are not always reserved. They're only reserved when they're in a particular spot. Okay. And the example we gave there was the integer, the word integer in Fortran is a reserved word or a keyword if it's at the beginning of a line, but anywhere else it's okay. Okay. Most languages just have reserved words, period. Talk about variables. Variables have these components. With the variable, you have the name, its machine address, its current value, its current type, because it could change, its lifetime, and its scope. Okay. The binding process. The binding process is when you're actually assigning resources to some construct in your code. Okay. So when that happens, there were some examples there. There was a Java statement we talked about in the notes. Okay. Things like the binding of the plus sign to addition is a design issue for the compiler designer. Okay. Other things like normal variables will typically happen at compile time. Okay. But then we also have dynamic variables where stuff doesn't happen until you actually run the program at execution time. Okay. So yeah, the static versus dynamic type binding. Static means it doesn't change in the sense. So in a language like C++, once a variable is declared to be an integer, it is an integer for life until it dies and gets recreated. Okay. Whereas in Python, they're dynamic. It changes when you assign something to it. Okay. There's also explicit versus implicit declaration of type. Some languages give you options. Okay, so I could say int x is equal, I could say int x, and I've declared x as an integer. Or I could say x is equal to 1. In some languages that works to implicitly do the type, right? So Python does dynamic implicit binding. You never tell Python what it is, but by what you assign to it, it gives you that, it determines the type, okay? So all variables have type, but that type could change. Okay. Some other categories here. We have the stack dynamic variables. Okay. So with the stack dynamic variable, they're statically type bound. Okay. This is what most languages use. So if you have an integer in your program in C++, it knows that it's going to be an integer. Okay. In most languages, Python's kind of the exception here, but in most languages, the amount of storage necessary for the different data types varies. Okay. So if it's statically bound, if the type is statically bound, then it can go on the stack because it knows how big it's going to be. Okay. So when it sees an integer x in a C++ program, it doesn't know what's going to be there, but it knows how much room it needs, right? So it's going to put that in the stack. Stack is organized. Okay. So the storage binding itself happens as far as when you say the x equals 5 or whatever. Okay, but the type is statically bound and it's put on the stack because it knows it's going to be there. Okay. So we also have the explicit heap dynamic variables. So these are nameless memory cells allocated and deallocated to the heap, and they can only be referenced through pointers. Okay. So the example of that is the new operator in C++. Those dynamic variables don't exist until the program's running. They're put in the heap, and those are the ones you have to delete yourself. Okay. There's also the implicit heap dynamic variables. They're bound to the heap only when assigned values. That's what Python's going to use. So everything is dynamic. The type and the storage is all dynamic. Okay. The scope of the variable refers to where it could be referenced. If it's static scoping, then you can look at the program prior to execution and know where it's going to be. Most languages have static scoping. Okay. Blocks. Different languages have way to do blocks, for blocks, else if blocks, whatever kind of block structures we have. So in C++, it's curly braces. Python, it's the colon and the spacing. So we typically allow scoping within blocks. Most languages do. Okay, which means if something's declared inside of a for loop, then that's where it will have scope. It will not have scope anywhere else. Okay. Remember also, global scope means something's declared outside of any of the functions. So it can be seen everywhere. But it's not illegal if you declare a local variable with the same name as the global. If that's the case, then you access the local always. Okay. So that's how that works. Dynamic scoping is based on the calling sequence of subprograms. I'm not going to ask you that, except to know that's an issue, because those are really confusing. And I don't like this. A lot of languages don't use those because they're just ugly. Okay. And then the referencing environment just shows at some given point in the execution of the program, what variables can you get to? That's basically all that is. Any examples I'll ask for will be in C++. Okay, so not everyone's had Python, so we'll just assume it's C++. Okay. We can also have named constants. And that's it as far as the material goes. Okay. But I did want to look at, let me pop it up over here so we can see it better. Just some examples. My pencil is going to cooperate. Of things from the homework that I think people may have had questions about. Okay. So if we have the following grammar, we're going to have not paying something to write at all. If S can go to A, B, B. Okay. And then A can go to A, B, or just B, and B can go to A, B, or A. Okay, so it's going to define our terminals and non-terminals. Okay. Then for example, let's say we want to look at the string B, A, B. So the first thing to look at looking at this grammar is what has to be the case. Okay. So we know it has to have an A and a B, right? Those are non-terminals in the very first line. So if anything that I would give you is A in the language, it's not. has to have one A and one B. Okay, and A has to precede the B. BA is not the language. Okay. So beyond that, if you look, the B's at the end, so the last character of the string has to be a B. So if that's not a thing, then it's not going to work. Okay. Then beyond that, can you have an A to the right of a B? You cannot. Okay. So all the A's are going to be to the left of B's. Is that correct? Maybe not. What's that? Right, that's right. But the order may not be. Okay. So let's look at this first, see what we can do. Okay. So we have to start, and let's do our parse tree here. Okay, so we're going to start with our S up here. Okay. And I'm going to have to get a B to begin with somewhere. Okay. And I get the B's from the A. Okay. I just need one B, so I can translate. I can use this form here. Okay. I want to take this A and convert it to a B. Okay. So that's going to give me a B over here. Now I have to do this first. I have to go to A. That's an A, it's done. This goes to a B. This goes to a B and it's done. Okay. So this A I can take to a B via this rule here. Okay. So BA, big B, B. Okay. So now to make this work, I only have to convert this B into an A, and through this rule, I can do that. Okay. So in this case, BAAB is a valid string in that language, and that's the parse tree. Okay. What are questions here? So what I do? Because you're older and you're smarter now. It is true that these things sit in your head, and you're like, what is that madman ranting about? But then at some point, hopefully before exam time, it sticks, right? This stuff is simple if you see the point, but if you don't see the point, either I haven't said it clear enough or you haven't thought about it enough. Okay. But that's all we're doing. Okay, it's a process. Okay. I know on the homework, some of you wrote out more of a linear format, as far as, you know, S goes to big A, little a, big B, little b. And on homework, that was fine. But on the exam, it's going to be on paper. So go ahead and do this graph. Yes.
Is this one with simple phrases? Regular phrases?
I don't think so.
There's a question on homework that asks for simple phrases.
Yeah. That was a weird question. I'm not sure 100% what that was. I will not ask something like that on the exam. I'm getting the homework problems from the book. I'm picking out ones that look good, but I don't always look at them close enough. And that was an example of that. Okay. So let's look at a different example here. See if I can back all this up so I can marks there. Let's look at B, 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 A, B. Okay. Is that going to work? Do we just know it's not going to work? We do know it's not going to work. What's that, Hunter?
Yeah, that's 2 A's.
Yeah, there's no way to get out of there without 2 A's, right? Because we have 1 A here, and this B has got to go to an A. Okay. In the same way, we're going to have 2 B's. Okay. So you could just say that right there. You could say, no, it's not valid because every valid string has to have 2 A's and 2 B's. Okay. But if you don't see that, okay, you can try to figure this out. Okay. So again, we're going to start with our S up here. And this should fail. If this doesn't fail, then we've done something wrong, right? It's going to go to A. It's going to go to an A. going to go to a B. It's going to go to a B. Okay. So if we wanted to, we could start down the path on the A's, and I could replace this A. Okay, I need to have 3 B's at the beginning. So this A can be replaced with an A and a B. And then do that again. Okay, and then one more time to get the 3 B's. I don't have enough room to get that. Okay. So now I have B, 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 A, B. Okay. Don't be tempted to think, oh, well, that's what we've got, B, 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 A, B, right? Because we still have this non-terminal. If we had the option here to go to nothing, we'd be good, right? But we don't. So that one's not in the language. Okay. You see that? Again, it didn't matter, and it doesn't matter to me whether you saw that without having to do the work or you have to do the work. Okay? Doesn't matter to me. The question is it valid? You said no, you've given me a reason. One or 2 reasons. Yes.
So there's another bar for like or like and that's VA that it's
Or nothing, yes. Or you could put null if that makes you happier, or I'll put on the example, I'll put null just so it's clear. Remember, nothing is nothing that knows it's nothing. It's intentional nothing. It's not that I didn't hear your question, I just didn't respond. There's a difference. Null has an edge to it.
left-hand side and the right-hand side.
What's that?
You can put the left-hand side and right-hand side so it's not the three.
Yes. Yes. Yeah, I mean, because you start on the left, you move to the right. Oh, yeah. I think I'm answering your question, but I'm not 100% sure. Okay. There are a couple others there, but I think you get the idea. Okay. So, for example, another one it gives us, which you can short circuit pretty easily as well. What about B, B, A, 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 A? Is that going to work? Nope, why not? Has to end in a B, this very first line. So no valid string is going to end. Okay, other questions on that one? Okay, so another question from that homework was asking you to design a grammar. Okay, and I forget how it's written down, but basically that allows any number of A's okay, with a corresponding number of B's. So A, B works, A, B, B, B works, and so on. Okay. It wants you to give a grammar rule for this. Okay. So if I have S goes to, what do I want to put here for my rule? AB is valid, right? So that's going to be one of the options. Okay, so I'm going to do AB as one option. I'll leave my pen right, so pencil writes. It's still not running. Okay, pencil. So that's okay. What else have to, how else can I build this? What's that? Yep. Yeah, maybe, but that's going to do what you want. Yep. Well, but you don't, it already does. That's an option.
Oh, yeah, right. So I see.
This is done, right?
Yeah.
Whenever I add, I'm gonna add to the middle with an A and a B. So it's gonna keep adding A's and B's, as many as we want. Okay. Could you get a more complicated grammar? Maybe. You could. If you do, that's fine. Okay. But that's the simplest way. Okay. Again, we're looking for the pattern and how to recreate the pattern. And simple tends to be better. Okay. So, what other questions do you have about anything? Yes. The what? Yeah, and it's the state changes. Operation, the big thing is it's going to make the state changes. What changes in state are there as you go through? Other questions? I had a lab assignment, but this took longer, so we're not going to have time. Sadly. We'll do it someday. So you got 10 more minutes. Are there any questions from the online crew? I should go ahead and put who's here and who's not. That'd be a good thing.
Nothing I can think of at the moment.
Okay. I think I will, hopefully if this records properly, I'll go ahead and release this video so you can watch it later. And you can use it if I give you something on the exam that I said I wasn't. Yes.
Will EBNF be on the test?
I mean, I guess it could. I wasn't thinking about it enough to put it on the review sheet. So if so, it's your fault because you maybe think of it again, but no. So that's Colton, he said it. No, let's not worry about that. I mean, it's good to know that it exists, but I'm not going to ask a specific question about it. The extended BNF format, that's where you can have the ranges of things. We won't worry about that. Life's complicated enough. Anything else from anybody? Yes. I think so. I think that in general, this is true just of classes. It typically is harder on the homework than it is on the test because of time and stress constraints. Okay? But I mean, some of these are pretty easy. I mean, what we just did, this stuff, yeah, that's quick. So the smaller problems, yeah. The things that are like the proving the program, it's too much on it. Okay? But other things, yeah, that's pretty much what I'm thinking about. There'll be different kinds of examples like that. Okay? Most of you have me before, not everybody. I'm not trying to be tricky. This is what you need to know, right? If you know this stuff, you're gonna get an A. We're all happy. I'm not one of those professors. It's like if you get an A, I'm unhappy. But if you all get 100, I'm gonna pat myself and everybody else in the back. Okay? I mean, it won't happen. But if it does, I'm happy. So take this at face value. This is what's going to be on the exam. Okay? It doesn't need to be a mystery. The question is, do you know? If you know it, we're all good. Okay? If you have questions this weekend, I will be around. Okay, not 24/7, but I will be around. The best way to get hold of me is to text me through my Google Voice number, which is on my door. It's also on the syllabus. Okay. So if you have questions, I will respond. Yeah. That's. Well, it depends on the question. I could ask you more a theoretical question about it or a practical question. And again, professors, if they give fair exams, which I hope I do, are going to telegraph what's important to them, right? We spend more time on axiomatic semantics than we did the other two. Okay? If I'm going to give a problem, it's probably going to be on axiomatic. Okay? It doesn't mean I'm not going to ask you about the others, but I think axiomatic is the most important of the three. the most practically useful. And again, that's my background experience. So yeah, the things that were on the sheet are what's likely to be on it. And again, nothing else is going to be on there. I didn't mention the extended BNF. It's not going to be on there. If it is, you can come back and say, look, I've got video of you saying it wasn't going to be on there, and I will give you the points. Okay, that'll be awesome. Other questions? Most of you got the homework turned in. If you haven't, I'm not at this point in the world being super strict on that. You do want to get it in before the exam. My bigger question, if the homework's not in, I want to make sure that you know where you're at, what you're doing. Okay. Because the exam is far more important than homework. So the homework's a good way to prepare for the exam. Okay. Anything else? Okay. Have a good weekend. Text if you need to.